Hello good people, I'm going to talk about orbitals and their energies. In the previous videos, I talked about energy levels or energy shells, the subshells that they are made up of, and the individual orbitals that can be found within these subshells. I also talked about how electrons occupy these orbitals and how each orbital can carry a maximum of 2 electrons. Fair enough. But how do the electrons choose which orbital to occupy? Let's say I have an atom with 8 electrons. Where will those 8 electrons go? Are they just going to randomly occupy these orbitals like so, or is there maybe some sense to them? Well, seeing how this is science and not magic, there is actually some sense to this. So the electrons will not occupy the orbitals the way I have shown it here. They will not just randomly occupy orbitals. It turns out that each orbital is associated with a particular energy level of its own. And the electrons will always strive to occupy the orbitals of lower energy first. In order to hopefully illustrate this, I need a better diagram. I need an energy diagram. So I'm going to get rid of this and bring in an energy diagram. Great. How do we interpret this diagram? Well, now, instead of using fuzzy spheres to indicate each orbital, I'm using these lines. So each one of these lines represents a single orbital. So at the bottom, we have the 1s orbital. That is the orbital with the lowest energy. Then we have 2s, then 2p, 3s, 3p, 4s, then 4d, then 4p, and then 5s. As we go up in energy levels, the energy requirements of individual orbitals end up being closer and closer together. So note that I have indicated a big gap between 1s and 2s, but once we get to 4s, 4d, 4p, and 5s, they're kind of smooshed together. I would also like to draw your attention to orbitals that have the same energy requirement. So for example, I have 3 2p orbitals, 3 lines, and notice that they are all level. This means that all of the 3 2p orbitals have the same energy requirement. The term that we use in science is degenerate. So these orbitals are degenerate. So now let's take an example and see how the electrons fill up these orbitals. I'm going to use oxygen as an example. Oxygen has 8 electrons. So now 8 electrons have to find a home on this diagram. How do we start? Well, there are 3 rules that we need to follow. The first one is the Aufbau principle. Aufbau is German for building up. And in essence, it means that the orbitals with the lowest energy are filled first. In other words, I start with 1s orbital. Alright, so I'm going to place my first electron spinning up. What happens next? Recall that each orbital can accommodate 2 electrons. So rather than going to the 2s orbital, the 1s orbital can take up an additional electron. And now we have 2 choices. I can either have another electron spinning up, or I can have an electron spinning down. Which one is it? Recall that each electron has to have its own unique quantum address. This is part of the Pauli's exclusion principle, which states that no 2 electrons of the same atom can have the same set of quantum numbers. So what are the quantum numbers for this electron here? N is 1, L is 0, ML is also 0, and MS, the spin, as I have drawn it, is positive 1/2. If I was to draw another electron that is spinning up, it would have exactly the same address. However, if I am to draw an electron that is spinning down, so let me erase this one and draw one that is spinning down, now the address would be 1, 0, 0, negative 1/2. The MS would be negative 1/2 because the electron is spinning down. And now Pauli's exclusion principle is satisfied. Each electron has its own unique address. That takes care of 2 electrons. Where will the third electron go? Well, 1s orbital is now full, which means we need to jump to the next level. So the third electron will occupy the 2s orbital. The fourth electron will also occupy the 2s orbital. The fifth one will go and occupy a 2p orbital. Where does the sixth one go? It has 2 choices. It can either pair up with this electron or occupy one of the unoccupied orbitals. This brings us to the third rule, and it is known as the Hund's rule, which states that the lowest energy is attained when the number of electrons with the same spin is maximized. In simpler terms, it means that when given a choice, an electron will occupy an empty orbital rather than pair up. Okay, with that in mind, the 6th electron will go here, the 7th will go here. And now the 8th has no choice but to pair up. Well, that is not entirely true. It could go to the next level, but that would require more energy. So it will actually pair up. And I'm going to place it here, spinning down. This now represents the electron configuration of oxygen. All of the 8 electrons have been accommodated, and we have followed the Aufbau principle, Pauli's exclusion principle, and Hund's rule. Let's do one more. So I'm going to get rid of the electron configuration for oxygen, like so. And now we are going to look into magnesium. Magnesium has 12 electrons that we need to accommodate. So we're going to start with the Aufbau principle, building up. 1 electron, 2nd electron following Pauli's exclusion principle. Then we move to the next level. 1 electron, 2nd electron, again following Pauli's exclusion principle. And now we get into the 2p orbitals. 1, 2, 3, and now we're going to start pairing them up. 5, 4, 6. The next one goes into the 3s orbital. Here it is. And the final one will pair up. Here it is as well. Fantastic. In summary, when accommodating electrons, we need to follow the Aufbau principle, which means we occupy the orbitals of lowest energy first. We need to take care of the Pauli's exclusion principle, which tells us that no 2 electrons can have the same set of quantum numbers or the same quantum address. And finally, we need to obey the Hund's rule, which means when given a choice of occupying orbitals of the same energy, electrons will occupy unoccupied orbitals first before they start pairing up. Actually, before I go, there is one more thing I would like to mention quickly. And that is, how do we actually write the electron configuration of an atom? So let's look at this magnesium. It has 12 electrons, and we have created this energy diagram for it. I can summarize the information of the energy diagram. So I'm going to write 1s for the 1s orbital, and then write a 2 because there are 2 electrons there. Then I'm going to write 2s for the 2s orbital, and then write 2 because there are 2 electrons there. Next, I'm going to write 2p for the 2p orbitals, and then write 6 because there are 6 electrons there. And finally, I'm going to write 3s and a little 2 to indicate that there are 2 electrons there. So this is now a written electron configuration of magnesium. I will talk more about these later. I bet you're looking forward to it. That is all for now, and I will see you on the flip side.